Alright guys, I'm gonna catch up to you. I'm in the ice cream gang up here all by myself. All by myself. And then region model, we had just talked about those. I really need overhead projectors. So what do you guys draw for this? I saw several people drawing things. You could draw a circle, or you could draw a rectangle. I like rectangles. They're just a little bit easier to break up. So I want 2 and 1/6, right? So I want to break this up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pretend like that's even. Okay. So I want 2 and this is this side. 1/6. Okay. So at this point, if a student can draw that, you can then ask them, one strip of this is worth how much? And if they're not sure, just say, why did you shade that in? What does that come from, right? That comes from the 1/6. Okay, that must be 1/6 of the picture. So this is what I pretty much saw. I saw some people doing circles and so forth. How do I get the the improper fraction coming from this? So the mixed number is pretty straightforward to do. How do I illustrate the improper fraction from this?
You can just count all the shaded boxes.
Yeah, sure. So how many sixths? How many sixths do I have? So I have 6, 12, 13. So it'll be 13 over 6. So I got 13 sixths, right? Thanks, Ron. As soon as the student understands that one of these strips is 1/6, then this would be 2/6. Got a little lisp. Does everybody get what's going on there? So what's really weird to me is if I just draw this, it's 1, correct? That is one thing. But if it was sitting inside of that, now that represents 1/6 of something. So it kind of depends the context of the problem I'm working within. Does that make any sense? And that's what's difficult for students to understand. It's sort of like that. I remember that one of the comics I love is this little kid is looking at the teacher, saying, yesterday you said X was 2, and now it's 7. What the shit? So yesterday you said this is 1/6, and now today it's 1/7. So it's that extra layer of, it depends on the context we're in, what this represents, right? You guys sort of with me on that? So this is established that it's all sixths. Gosh, I'm really having trouble saying that today. So that's why this one thing represents sixth, and I can just see how many sixths do I have. I love it. Is that cool? Okay. These gave us some trouble. We weren't exactly sure what to do with these, and I think it's because I did the teacher thing of a very easy example, and then I gave you these. But the idea is just to break them down. If you find out they have a part in them that cannot become some kind of 10, then it's screwed, right? The only numbers that could become 10 when you multiply them together are 2 and 5, right? Single digit numbers, be careful because somebody can say, well, 10 and 1 jump. Single digit numbers, 2 times 5. That's it. You guys agree with me? So if it's got a 3 in it, if it's got a 7 in it, if it's got whatever, it's screwed. So this first one, whatever way you think to break it up, so is that one going to work? Will that one be terminating? Totally. What would I have to, and this is the extra layer, what would I have to multiply top and bottom by to make it become immediately something that's a decimal? To make the bottom become some multiple of 10?
3.
Say again?
3.
No. See these two? Don't they make 10? How do I make 2 more 10s? What do I have to multiply? Each of those 5s needs its own. It needs its own 2. So I got to multiply by 4. And sure enough, what's 4 times 250? 1,000. So you get 36 over 1,000. There's your terminating decimal. You guys with me? So every terminating decimal is going to be over some power of 10. And that's why this approach works. What's wrong with 280?
It had a 7 in it.
Yeah, okay, thank you. It's got a 7. That's a beautiful way to say it. There's no way it could work. It's got a 7 in it. It's got a little extra dude. I can't multiply 7 and get 10 using a whole number. So it's never going to work. It cannot be a terminating decimal. I don't know if anybody tried to throw this in your calculator, but I have no idea what it is. Something gross. Okay. And then, of course, this guy, I don't know if anybody noticed this is a power of 2. It's the power of 2. Yeah, 128. So you got 2, 4, 8, 16, 32, 64, 128, right? You guys all with me? So if you break this down, 2 times 6 is 4, 2 times 9, 2. And then 32 is 2 to the 5th. That's really good to memorize. So then you get 5, 6, 7. You get 7 2s. So will this be a terminating decimal? Yes. And then if I ask you a further question, what do you have to multiply by to make it over some power of 10? What would you multiply by? 7 5s, 5 to the 7. Because each 2 needs a 5. Aw. Okay, maybe. Okay, is that idea good? Okay. This one I think was everybody's favorite. There's 2 main answers, and then, I don't know, beyond that, maybe there were some other answers, but did anyone think they got the answer for that? Yes, what you got?
Only fractions have a multiplicative inverse.
Beautiful. So if I ask you, if I'm talking about whole numbers, what would 4's multiplicative inverse be? Is it in the set? If I'm talking about only the set of whole numbers, is the multiplicative inverse of 4 in there? What is the multiplicative inverse of 4? Man, having trouble speaking today. What is it, sorry? 1/4. It's not in the set. It doesn't even exist as far as whole numbers know. That's why we didn't even talk about the idea of multiplicative inverse until we got to fractions, right? So that one was, to me, if anything was going to be at all obvious, it would be that one, because that property didn't even come up until we got to fractions. The other one is a little bit weird, but I would accept some kind of closure, where you define division by something not 0, right? So division by a non-zero whole number. That's not closed for whole numbers, but it is closed for fractions. Does that make sense? No? If I have a set of fractions and I divide any of them by a whole number, is it still a fraction? Yes. I love you guys so much. So if I take any fraction, 7 over 11, and divide it by 2, now it's 7 over 22. It's still a fraction, right? So non-zero whole number. If I take a whole number, the set of whole numbers, and I divide 2 of them, is that still a whole number necessarily? No, 8 divided by 3, not a whole number. So that, you could argue for kind of a more restrictive definition of division. But the easier answer, I think, was multiplicative inverse. Yeah, okay. Now, I'm not saying whole numbers don't have multiplicative inverses. I'm saying if your set is only whole numbers, multiplicative inverse doesn't even exist. It doesn't hold. Okay. This one. So back in the day, way back when, we did 3 times 5. Remember this? And we had 3, 1, 2, and we had 5, 1, 2, 3, 4. Okay. And then you can just count 1, 2, 3, 4, and you get 15. It's amazing. So it's just that same idea, just kind of like taking to the next level. We add in the idea of shading. So if I do 2/3 times 3/4, bless you, how would I represent 3/4? And I want to go this way. So I would just slice this sucker 3 times. And 3/4, is that cool? And then if I put 2/3 over here, so now I kind of ignore the shading that's there already. Just cut this whole thing into 3 parts. Right? And then shade in 2 of those. What have I got there? 1, 2, 3, 4, 5, 6 over what? 12, which reduces to what you guys should have known in the beginning, right? What does this reduce to? 1/2. And of course, right here, 3's canceled, 2 goes into 4 twice, you should know it was gonna be 1/2 from the beginning. Okay, maybe. And again, one fundamental way to explain why this makes sense is not even mathematical, it's just how much of the picture is double shaded. Well, 6 of them, so half of them are double shaded. So of course 6/12 is the same thing as 1/2 of the picture being shaded, right? Do you understand? That's not even divided by 6 to make it one. No, it's just, what's another way to say this? Well, half of it's shaded. So of course 6/12 must be the same thing as 1/2. And then of course you can start saying, well, if you divide by 6, you got what over? Okay. Then you get more computational. Okay. All right. So here's Jeff. Good old Jeff. This is something I've seen just about every level of math I teach, including like differential equations, which is the highest level of class. Something equivalent to this mistake. I saw one group, I looked at this, I didn't look at everybody's answer to this, but I know one group got this right. What, is this correct? I think I've made it pretty clear. If anybody said yes, and now you're changing your answer. What did I do wrong?
Squared.
Yes, so this is not that hard of a thing to tell, but again, a huge part of teaching is understanding what your student did. What did they do? Was there any logic in it? Can you see why they thought they should do that, right? That's what the good teachers do. The bad teachers go, it's wrong, what are you doing? Well, maybe not, that's really bad. How would you explain this to me, little Jeff? What do you mean it's wrong? Yes?
When you square 2, you're multiplying it by 2.
Okay.
And when you square 3, you're multiplying it by 3.
So you explain, because at this point they understand exponents.
Mm-hmm.
So this is 2 times 2 and this is 3 times 3. Now where does that lead? Why is that wrong? What would you tie that into?
You have to multiply the numerator by the same thing as you did the denominator.
Exactly. Now can somebody else tell me why that must be true? Sure.
Because we'd be multiplying in a sense by 1.
Beautiful. So this is no good because I am taking the original number and I'm multiplying something that isn't 1. Therefore, I've changed the number. I rejected the reality of what was given me and I've replaced it with my own. It's no good. So what I see a lot, I don't know if I think I had one handout that did this. We'll do stuff like this. Let me see if I can do it better here. No, you're not going to do it really well. It's just the big 1. Kind of like the number 1. It looks like half of his shirt. So, wearing my shirt. Okay. So you make this big ass 1, and the point is, this is really difficult to understand when you first see these things. If I write 4 over 6, why in the hell is that equal to 2 over 3? I mean, when I'm first working with this, I'm like, what do you mean? Because it looks like I'm saying 2 is 4 and 3 is 6. So this whole idea is nowhere near obvious. But when you talk about, I mean, hopefully not a lot of people are just throwing this in the calculator and saying, hey, look, see, it's the same decimal. Right? So the whole idea is if I'm able to reduce it back down, then it would represent the same number. I am just dividing out a 1. Right? So there's a connection to be made between when you square. So I love it. I love this progression through people. When you square, you're multiplying by different things on the top and bottom. Meaning, overall, you multiply by something that wasn't 1. Meaning, you took the original number and changed it. It is now 2/3 of what it was. There's no way it could equal that. Okay, maybe. All right. And then everybody's second favorite problem, this guy. So I had a group in the back that sort of like, actually sort of re-engineered the reason this works, which I love. Can somebody else tell me what you guys, did anybody else try this one? You tried it? What'd you do?
I moved the decimal places.
So tell me exactly what to do. Sorry. So I'm right here. What do I do?
So
So I moved the decimal places, being added to twice,
Okay,
and then I did that to the four as well.
so move it twice, so what happens here?
I added a zero.
Okay,
And then just-
so I was hoping, I was curious, and I know it's been a while, right? I was curious how many people would remember that algorithm. And then, because then I wanted to say, why the shit does that work? So, what the original problem, what does it look like as a fraction? It's not even a fraction really, because it's got decimals in it. What does it look like as a ratio? What is this, what am I doing? How do I write this as a ratio?
2 and it's 11.
No, not individually. Just, if I have 3 over 7, isn't that 7 into 3? So I mean, what is this? Take it back to a ratio. What am I dividing, and what am I dividing it by? I'm dividing 78.4 by 0.02. Okay, that's it. That's all. Just make it a ratio, right? You guys all with me? So here's why the shortcut works. And I like one student called this the loop method. Loop, right? So whatever the hell, whatever you call it. Why does it work? Why is it legal? Why does it come out to be the right answer? Well, because what am I allowed to multiply top and bottom of a fraction by? As long as it's not 0. So I can multiply top and bottom of a fraction by any damn thing I want to except 0. So if I wanted to, I can multiply top and bottom by 111.783. I wouldn't want to, but I could. So here, I would much rather divide by a whole number, correct? So I really just wish this would just, these decimal places wouldn't be here. So what would I multiply by? 100. So make it move over once, twice. And of course, whatever I do to the bottom, I've got to do to the top. So very often, when students get to the level of doing long division, they have kind of lost the connection between written like this versus written like a ratio. Right? I'm just realizing this is a pencil. It's kind of not coming through well. If I write those as, does that by itself make sense before I do the next thing? Do I have a pen? You have a red pen. You have everything. Okay. So I got 78.4, 2 times 100 times 100. So I mean, that becomes the shortcut up here. When I multiply by 100, I just move the decimal over twice. And then how would you explain to a student where that 0 just sort of magically became existence, right? Into existence. Where was that? It was in another dimension. At this point, hopefully at some point you've talked about the fact that, just like we did, we talked about 0.1 being the same thing as 0.10, being the same thing as 0.100. So they sort of should understand there are an infinite number of zeros at their disposal, right? So of course, if I have to move it over twice, one of these zeros that sort of are invisible comes into being, right? Steps up. Oh, call me in the game, coach. All right. So I have written so much there. So the shortcut is once, twice, once, twice. So now that becomes this, which is much, much easier, right? So you should get 3920. Yay. Okay. Now real quick, what would this look like, let's see, as pure fractions? So I got 78.4 divided by 0.02. What is 78.4 as a fraction? Improper. What place is it in? What place is it in? The last digit's in the tens place, so 784 tenths. 784 tenths. Yes? Divided by? 200s. How do I divide fractions? How many hundreds cancel? How many tens cancel? So 10 goes into 100 10 times, right? So do you see how I get 7840 divided by 2. You see that? So a lot of these algorithms, which are shortcuts based on longer approaches like this, right? So I was kind of hoping, and again, it's been a while, so at least one person remembered the move the decimal the same number of places. But at this point, you've definitely forgotten why that even works. It's just sort of like something that you would do automatically, right? But for a student, it's fine if later in life they forget, but when they first learn it, they have to have something to build it off of. And of course, when you get to decimals, you're going to build a lot of what you're doing off of fractions, because that's what you will have just been discussing right before decimals. Okay. My God, I can talk a lot, I know. Okay. Any questions from this little thing here? All right, so what I want to do, I'm going to give you guys the practice test. We're going to talk about section 7.2. This next test is going to only go up to 7.2. So only through 7.2 homework will be due. And then we'll head out as soon as I'm done with 7.2. I like everybody sort of swivels around. Oh, so we actually already discussed a couple things from 7.2. Of course, with me, all right, so a couple things I do that aren't necessarily the best thing to do as a teacher. I very often don't know what section I'm in. I'm a little better in this class because I think I told you guys this is the 3rd time I'm teaching this, so it's a little. But if I'm teaching like pre-calculus, I just know the ideas. And then a student's like, what section are we in? I have no idea what section we're in. I'm really sorry. So, be better than that. But last time we did a couple of things that come out of 7.2. One of those things was, like if I wanted to add oh yeah, sure. Yeah, okay. If I wanted to add these two things, and I want to do it using fractions, that's basically what we just did, but we did it with division. What would that, obviously, kind of tells you where to start, right? And normally we would do, it doesn't really matter. You could do mixed numbers or improper. It'll work either way. In fact, let's try mixed numbers this time. So how would I write these things as fractions or mixed numbers? This would be 42 and 1/10 plus 2 over 100. I love it. So before you can add those, what do you have to do actually? All my markers are dead. Anybody?
Make it improper.
You don't have to. No, definitely not. Definitely not. In fact, I don't want to. Nah. No, sorry. Yes. Yeah. So 42. It's just sitting there. 1/10 and 200s I can put together. Don't forget, what's between 42 and 1/10? What's between those? What's understood to be between those? Addition. So I'm going to add stuff that I can add. And I can add 1/10 and 200s almost. What do I have to do? Yeah, multiply by 10. So it'd be 42 and 1, 10 hundredths plus 2 hundredths. And then you get, crazy enough, you get. And what is that as a decimal?
42.12.
Yeah, 42.12. Now, write that down, 42.1 over 0.02, and add them together by hand. So just add the decimals straight up. So again, we talked about this last time, we have to be careful about what? What needs to line up? Decimal place. What do you think a student would have trouble with the first time they're doing this? What do you think would kind of freak them out a little bit?
There's nothing above it.
Yeah, I'm adding 2 to empty void, right? What is empty void plus 2? So what do we put here? How does that relate to what we did over here? That step of adding a 0, which we have no problem doing, but they need reinforcement constantly, that that's legal, it makes sense. Where does it come from over here?
Multiplying
Yeah, when I multiply this by 10, it did pick up another 0 right there. You can sort of, that's why it's really good. Again, building a new idea off of something they already have worked with, right? And you can show them, see that idea? It's right there. That's exactly what you're doing, just in more concise way. So that is just this shortcutted. Okay, I like it. Shortcutted? Is that a word? No. And then we get, incredibly enough, thank God, the same. Okay. I like it. Okay, that's ground shaking. And again, reinforcing for you guys that idea of building off of stuff they've worked with already. What was the other thing before I do this? Oh, yeah, okay, nothing major. So what about, we talked about this before also, what if I wanted to multiply those two numbers? Using fractions. So now the problem is multiply. One thing as a teacher, you want to develop your sound effects for various. So for me, multiplication is. So if I want to do this as a fraction, and again, this one is this was definitely easier if I write them as what kind of fractions? I don't know. It would be easier. What kind of fractions would be easier? Yeah, make it a little more compact, so make it improper. So students have trouble with this, and I feel a little hesitancy on your part, some of your parts too, about how to make that into an improper fraction, but it totally is determined by the last digit. That's in the tens place, so it's 421 over 10. Don't even have to think about it. And real quick, just in case, that's 42 and 1/10 like we did before, correct? 10 times 42 is 420 plus 1 is 421 over 10, so it's the same thing. Okay, and then times, what's this dude? All right, so what do you got on the top? What do you get on the top? 842. And what do you get on the bottom? 1 with how many zeros? 3. And what is that as a decimal? Yes, and the number zeros tells you how many places to go back. That really kicks a lot of ass. And of course it should be that easy because I'm working with tens in a base 10 number system. So of course it should be that easy. Now, how would that go? No, take a minute. I'll do the same thing I did last time. Go ahead and do that by hand. The full out straight up algorithmic way. Do I have to worry about lining up the decimal now? No. Do you understand why not? Did we have to get LCD here? Did we have to get LCD here? Nope. Multiplication, a lot more laid back. I told you that last time. I can't add x and x squared, but I can multiply x times x squared. Multiplication, a lot less like uptight. So I can just put down there 0.02. Go for it. So of course, the first step is forget the decimals, right? Forget they're even there. 421 times 2 is 842. That's crazy. Now you got to go, okay, there were decimals there. How do you, we talked about this last time, but just remind me. How do you figure out where to put the decimal?
You see how many numbers are behind.
Yeah, how many decimal places? 1, 2, 3. Now, can you relate that shortcut to what we just did over here? Each decimal place is related to what here? How many decimal places were there in 42.1? 1. And how many zeros are on the bottom of it when you write it as a fraction? 1. And each zero on the bottom relates to move the decimal back 1. Yes? Do you see how it kind of, it's this big circle? Okay. So each decimal place would relate to how many zeros are on the bottom of it as a fraction. At the end, you would just collect all those zeros together, and that would tell you how many places to move it back. So if I just count 1, 2, 3 places, I have no reason to make them fractions. I could just jump ahead to say, oh, that would have 3 zeros. I'd move it back 3 places. You guys, again, this is not intuitive. And you do not want to tell a student, yeah, you just count them. Just count them, shit. Just do it. Well, especially don't say shit. Right? Don't model, but I'm teaching college. It's very different. Yeah, but you need to give them a foundation to live on instead of just this is the process. And that's, I see this all the time. Students get to higher levels of math. They've had teachers that just tell them this is how you do it. They just feel like math is made up shit that people just decided this is the way it goes. So that's how they look at mathematics. And that's why they think they have to memorize everything. Because if you believe math is just a bunch of made up shit, there's no reason it should be connected. Do you understand what I'm saying? So if they understood from the beginning, no, everything we do has got to have a purpose, it's got to have a meaning, it's got to be something you're going to explain, then they start to make connections better, right? Okay.
Blah, 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 blah.
Oh yeah, we talked about that one. We talked about, here, let me see. Yeah. Here, let's do this. Okay, so I brought this up last time, and now in this next section it comes out fully as an idea. Scientific notation is just a way to rewrite a number into a problem that would become that number. Not surprisingly, at this stage in the book, it does not have negative exponents. Because at this stage in the book, we're supposed to not even know that negative numbers exist, right? I don't know if you guys are aware of this. I know we've been subtracting, but that's an operation, right? That's not a negative number yet. But I just want to say real quick, 4,000 get this, that's 4 times 1,000, that's crazy. And what's a more concise way to write 1,000? 10 to the what? 10 to the third. So this is the scientific notation that represents this number. And it's not just notation, it's actually a little problem that works back out to that number. So if I multiply by a certain number of tens, of course I get bigger. So let me tell you a little story about young Jeff. Young Jeff did not understand left and right. I could not keep it in my head. And I still, sometimes when I'm driving and somebody's giving me directions, I have my hands like this because the L is the left. Jeff does not mind. Jeff is talking about himself in third person, which is really cringy, but too bad, it just happened. I don't mind telling you this because I know a lot of other shit, so I can live with me not knowing that. I also had trouble between yellow and white for some reason. Now I'm sharing too much. So I always hated it that they would teach scientific notation left and right. If you got to move the decimal left, then it's going to be No, that's dumb. It really is dumb, and not just for the kids like me. I don't know. Positive power means big number, because that would be actually multiplying by that many tens. So of course it gets big. I don't have to think left or right. I just have to think big, right? So for example, what's this? What's that as a fraction? This is why it doesn't make sense the book doesn't talk about this, because it goes right into decimals and fractions. What's that as a fraction? 4 over 1,000. And we just identified that 1,000 is 10 to the third power. And I told you guys the book didn't. How can I bring that 10 to the third up? What would have to happen to the power? Do you guys remember? Certain kind of power that would tell me to flip it. You guys remember? What is x to the negative 2? One over x squared. Does that, you remember that? Negative power means flip. You guys remember? We actually proved that very quickly. X squared over x cubed. If I subtract 2 minus 3 is negative 1. If I cancel 2 x's, I have 1 x left on the bottom. X to the negative 1, 1 over x, negative power means flip. Not really proof, but it's close enough. Okay. So this would be 4 times 10 to the negative 3. So I really want this to make sense. Negative power means flip. So I'm actually dividing by 10 3 times. So of course I get small. I don't have to think right, left. Positive exponent big, negative exponent small. Bam. Okay. So what do you guys think about this? What am I writing? This here. Let me start with this. I'm going to do a little bit of algebra and see if you guys are cool with that. What would that be? A little bit of algebra for you. A little amuse-bouche of algebra. I watch too much Top Chef. Amuse-bouche. All right, who's got it? Who's got the answer? I know you. So hold on. Anybody else got the answer? Sorry, Ryan. No? Do you guys have an answer? You're just not sure if it's the right answer? Yes?
16x to the fifth.
Close. Gotta be careful though. 4 times 8.
Oh, no, 32.
You're good. All right. So 4 times 8, 32. 2 x's, 3 x's, so of course we get 5 total, right? Is that all right? Okay. So is everybody cool with that? Even if you forgot it, you weren't comfortable, but you remember that? Of course that's how that works. What's the only operation in the whole damn thing? Only operation up there. What's the only operation up here? Multiplication. I love it. I know there's exponents, but aren't they based on multiplication? Totally. Only multiplication. I could do that shit whatever order I want to. I don't know what 4 times x is, so I definitely don't know what 4 times x squared is, but I know what 4 times 8 is. So of course I do the multiplication of the shit I know what they become, right? So, what does that have to do with this, Jeff? I don't know. Oh yeah. What would this do? 4 times 10 to the 5th times 4 times, 4. Let's do 2 times 10 to the 7th. It's pretty much the exact same idea, right? So what do I know how to multiply here? What is 4 times 2? It's crazy. And what is 10 to the 5th? 10 is 5 tens times 7 more tens. Makes 10 to the 12th. Beautiful. What would you say to somebody who thought that was supposed to be 10 to the 35th? What did they do? How would you explain that that's not what you should do? Because I don't blame, even somebody who knows how this is supposed to work will put 35 sometimes. I've done that kind of shit before. Sure, my brain just says times. Yes?
Is 10 to the first means there's 5 tens and then 7 tens?
Yeah, so if you had time, you want to show a little kid, you write 10 5 times, and then you put 7 more 10s, and you say, how many 10s are there? 12. Okay, beautiful. So that's why. And the way I like to say it, and this might freak little kids out, there's no 5 anywhere in here. There's no 5 anywhere in this whole thing, right? And when I say that to some on there, this one kid's looking at me like, you feeling all right? Because of course it's not a 5. That's not a 5. That's 10 5 times, right? So to say it's 35 makes no sense. There is no 5, there's no 7. How'd you get 35? There's 5 10s, 7 10s, so 12 10s. Okay. So let me ask you this. The original problem was made up of 2 scientific notation parts, correct? And the answer is scientific notation, right? Let me ask you this is this in scientific notation? Is that in scientific notation? So here's something, let me see how you guys feel. I admit this is really weird, but I like to think of scientific notation as a 10 vampire. It likes to suck all the 10s out of something. Doesn't 11 still have a 10 in it? So this is not scientific notation. It's supposed to be a number between 1 and 9, and maybe decimal something, times a certain number of 10s, because I've taken all the 10s out of it. So let me ask you, how would I change this into scientific notation? What would this want the decimal to do? It would move it. It would make the number big, yes? It would move it that many times. Where should the decimal be so that this is in scientific notation? Where should the decimal be? Between the ones. Between the ferns, no. So, I really want this to make sense. I'm going to show you 2 ways to do this. This is the way I do this. This wants it to move over 11, and it's currently right there. So if I force it back 1, now how many times does it have to move that way? 12. I've just added more work to the poor little dude, right? So this would equal 1.1 times 10 to the 12. Another way to do this is to write the 10 to the 11th here. And now how do I write 11 in scientific notation? And I'm just realizing I didn't talk about the shortcut yet, but how do I do scientific notation? Don't I have to move it back once? So that would be times 10 to the 1st. And of course, what do I get then? Same thing. So you can either do it more mathematical. It's kind of funny that the math teacher does it as if it's a little story instead of the mathematical way, but I've sort of always been that way, to be honest. I like the idea of, I've got to do this much work. You pushed it back 1, you asshole. Now I got to do more work. Okay, maybe. So, with all that said, you guys do this problem. I want you to change it to scientific notation, do the multiplication, and make sure your answer is in scientific notation. Everybody with me? Okay. And then I'll show you a shortcut, how I would do this problem, if I was allowed to. So remember, I want you to first rewrite these in scientific notation. to catch up to you guys a little bit. This would be 4 times 10 to the 12, right? 3, 6, 9, 12. Yeah. And then this would be 3 times 10 to the, yeah, 2, 4, 6, -6. I like it. So when you multiply your numbers together, you get 12. And when you multiply your 10 stuff together, you get, good, because you add powers. Is that in scientific notation? Nope. So it should become 1.2 times 10 to the 7th. Kick ass. Now let me show you, this is kind of cool. Remember when we do division of decimals, we do the loops, but we do them in the same direction. Because it becomes a fraction, I've got to do the same thing to the top and the bottom, correct? Do you guys remember compensation? What was compensation again? What was compensation? Yes, so watch this. If I took a certain number of 10s, every time I multiply this by 10, won't it become a bigger number? So if I do 1, 2, 3, 4, 5, I'll have to do 1, 2, 3, 4, 5. So I took these multiples of 10 and multiplied these by them. Does that make sense? Or I can even go one more, I guess, if I wanted to. But yeah, let's go one more. Sure. One more. There. And then I can do 4 million times 3. I'll end up here, and then I can move the decimal back. So you can sort of do, so it's funny, when you multiply two numbers, if one gets bigger, the other has to get smaller, so it's the same number. So 4 times 5 is, that's crazy. 4 times 5 is 20. If I make 5 10, 4 has to become what? So it's still 20. 2. So when I'm multiplying numbers, if one gets bigger, the other has to get smaller. When I'm dividing two numbers, they have to get bigger together or smaller together. Is that? Okay. All that last thing I just did was extra, though. That's just the way I sometimes do it. I like to think of it as so many zeros here eating so many zeros here, and you just deal with whatever's left over. Oh, we did that already. That's awesome. So what about this? Last problem for the day. Then we'll leave a little early. Why not? What if I want you to do this same way? Change to scientific notation. Change to scientific notation, and then carry out the operation. So change the top and bottom to scientific notation. Do that first. Yeah. Yeah.
When the decimal is 4 and a bit, it becomes a negative.
Yes. If it starts the way I keep it in my head, if it's a small number, it's going to have a negative power. If it's a big number, it's going to have a positive power. Yeah. Because again, young Jeff, left and right, it was rough. Jeff now. So what do you guys get for the top? Scientific notation. Yeah, 3, 6, 7. I love it. Gotta love our system of commas. By the way, I haven't said this yet, but in some countries, the comma and the decimal point are reversed. So if they wanted to write 0.004, that's how they would do it. And if they wanted to write 1,000, they would write it like that. So that's something I had to be aware of as students came in from other countries, that this is an extra thing for them to worry about as they try to get acclimated, right? So you're gonna have to actually worry about the same thing. You might get some families who are refugees or who just moved here or whatever, and the students sort of did some math back home and they're used to something very different. And that's just an extra layer that they have to worry about, right? On top of probably learning the freaking language too. What's the bottom become? Good. Now, 4.8 divided by 4. Yeah, 48 divided by 4 is 12, so 4.8 divided by 4 is 1.2. What happens here? You do? Yes. So the way I do this, what's a negative power mean? It's a 4-letter word, starts with F. You can say it in mixed company. Flip. You guys with me? Negative power means flip. So these 3 tens go up. How many tens are up there already? So 3 more, 10. Or, like Morgan said, 7 minus negative 3 is 7 plus 3 is 10, but it's so easy to make a negative mistake when you do it that way. So I just like to move all my negative powers first. Now they're all positive, I'm not going to make a negative mistake. Blush. I gave out the practice test, right? Yes. So that's enough, guys. That's plenty. So Tuesday, we'll have the review day. I'll have the answer key for the practice test. Thursday's our test. My little Thanksgiving gift to you. Because then the next week is Thanksgiving. A whole week. Yay. Huh? Yes. All right. All right, guys. Oh, yeah. That's all right.